Good afternoon, everyone. Welcome to the Mind Action Series Life Sciences webinar. My name is Rizal Lowe, and I'm the Sales Manager at Mind Action Series. Our presenters today are Lorraine Keane and Susara Norkia, and they are the co-authors of the Mind Action Series Grade 10 Life Sciences and Grade 8 and 9 Natural Sciences textbooks. Please take note that we are recording the webinar and we'll share it afterwards with everyone. So if you must leave, you will not miss anything. We will also share today's PowerPoint presentation with the recording. If you have any questions, please type them in the chat box and we will answer them there. So let's get right into it. Over to you, Lorraine.
Right, Roselle, thank you. Hello, everybody. I'm going to turn my camera off. And as you can see on the screen, we're talking about the history of life on Earth today. And please, while you're coming in, Roselle will continue to admit you. Those of you who have friends who wanted to join, we will, as Roselle has said, the material will be shared. The good news is that we have already prepared some questions on the topic of today with memoranda in Afrikaans as well as English. The PowerPoint will be released in Afrikaans as well. Then you can either use it as is or mix and match. The matric session that we had on genetics earlier this year, the PowerPoint has been translated, and in Wellington, we had an unplanned power outage from 8 till 4 yesterday, and my plan was to finish the grade 12 questions and examples of genetic questions. So yes, at last, that is also ready. Now, in the CAPS document, the history of life on Earth starts with the beginning of life on Earth. And this is what the grade 10 work on evolution is all about. And in grade 11, the evolution that we do is the development of plants and animals and their relationships. And then in grade 12, as you know, the grade 12 curriculum is based on the theories of evolution and also on human evolution. And we might have another workshop on human evolution. Most of you will do that only next term. So yes, we might be there. Right, let's get started. Just a little bit of commercial news. For everything that we do in this session today, there are examples of questions and also other examples of the topics that we discuss. So please go and look at the Mind Action book. I'm personally quite excited about some of the way that we explained aspects, such as with biogeography, the distribution of our ratites, guinea fowl and pheasants, etc., all of them over Africa and other continents. But let's get started. The first thing that we need to talk to our learners about is what is evolution. And we know that the term means development, changes. Now, evolution is a difficult subject in some communities because there's still a belief that evolution wants to stand against opposite religion. And we know it is not the case at all. And I'm not going to go into that discussion today, but please make sure that your learners understand that the topic of evolution in their textbooks, number one, is about science, and number two is compulsory to know, to learn, and to write exams and tests on it. And you will see that Susara is manning the chat group, and please ask your question, give your comments. She will stop me if there is something that we need to discuss further. Now, there we've got it. Evolution is a natural process. It's a change of organisms, all through organisms, generation after generation, over millions of years. Well, we'll talk about that time frame. Now, it's controlled and driven by changes in the physical environment, and then it will allow some species to flourish and change while others will perish. We know about natural selection. So let's say that changes in the environment drive natural selection, and natural selection drives evolution. You've got that? Changes in the environment will drive natural selection, and natural selection will drive evolution. Okay. To talk about the history of life on Earth, we have to see where it all started. Evolution now. Now, we know that the Earth is about 4.6 billion years old. Researchers time and again will discuss that the Earth might be a few million years older, but this is the accepted number at the moment. Interestingly enough, I will never forget this number because it was ultimately established, the age of the Earth, by a man called Claire Patterson. And his name is spelled like the female Claire. But yes, Claire Patterson did a lot of excellent work. And as far as we know, life started about 3.6 billion years ago. Once again, this time is pushed back slightly, and every now and then we see articles about that. People, I would like you to recommend two things. That number one, you use social media, you use the internet, you use libraries to read about evolution. It's a fascinating topic. And just mind the fake news, like we had yesterday and the day before, about the phenomenon that is now supposedly moving the sun 132,000 kilometers further from the Earth. So that's why we're going to have a cold winter. I hope we have a cold winter, but the sun is where it should be. Then one thing that we should remember is that life started as very, very simple organisms, unicellular, single-celled organisms, until today we have very complex organisms. And yes, evolution is still occurring day by day. When we talk about a geological timescale, first I must say that your learners do not have to study it. Now, when we talk about the stages of life, long time ago, with the beginning of the origin of the Earth, we talk about the Precambrian time and the Cambrian and later periods. So we can actually divide the timeline into these two periods or time slots. When we talk about the stages of life, go to the Archean, the Proterozoic, and the Phanerozoic. And that is actually where we have the first vertebrates and land plants, etc., etc. But you can see what's happening here. This is another way to put the geological time scale. Here you can see on the left millions of years ago. Now this is about later life, where we have many fossils and where we can recognize fossils and where we know when they originated. And we talk about the Paleozoic, the Mesozoic, and the Cenozoic, which is also the area in which we originated, with a period in the Neogene. Yeah, once again, because of the damage we are doing to Earth and to the ecosystems and changing organisms, new names are being given to these times. But here you can see, and remember, our learners do not have to know all these details. Let them know the Paleozoic, the Mesozoic, and the Cenozoic eras. Let them know important times, such as the Cretaceous, which was the time when the dinosaurs started to become extinct. Or let them know before when the Cambric and after the Cambric explosion. But they don't have to learn the timeline. It will be a good idea if you can use a similar timeline and let them answer questions about it. In other words, accessing information and choosing it. Also a necessary skill. Now let's get started. About 4 billion years ago, 4.56 billion years ago, life was rough, woes en leeg. The Earth was constantly bombarded by meteorites and comets, volcanoes all the time, tsunamis, oceans covering just about everything. The temperature on Earth, everything in those times from 50 to 80 degrees Celsius. Interestingly enough, the atmosphere contained carbon dioxide, water vapor, and nitrogen gas. Much like today, apart from the absence of oxygen and the concentration of water vapor in the air. But keep this in mind. Then undersea hot springs, we also call them black smokers, they released scalding steam into the air. Where did the heat come from? Well, these hot springs came from cracks in the Earth's surface, so the heat came from the inside of the Earth. So there we have it. Now, I have to say, many of the diagrams and pictures that follow now came from a presentation that I attended with the Teaching Biology project that was done by Dr. Roger Smith, research paleontologist, so I have to credit him for this work. Okay, and so it went on and on and on. And about 3.9 billion years ago, we know that life started around these hot water spouts on the ocean floor, these geysers. And it started as molecules. The thinking is RNA molecules first, and then cells forming, containing this RNA. And that was the time of Luca. Now, not a very popular name amongst boys and girls these days, but LUCA, Luca, the last universal common ancestor. Because from there, life developed into very different directions. Okay, so organisms slowly started. Microbes, that is the time of the archaea, the very, very ancient microbes. They used the carbon dioxide and the chemicals near the hot springs. They used those as energy sources, so we had chemosynthesis. So they used the chemicals to chemosynthesize. The chemicals mostly things like H2S, hydrogen sulfide, for example. That was the time of the eubacteria also. They used carbon dioxide, as I said, hydrogen sulfide, and then a light capturing molecule. Not chlorophyll as we have now, but they used a light capturing molecule to start photosynthesizing. The cyanobacteria, the blue-green algae, were now about 3.8 billion years ago, not totally replaced, but they used water then instead of hydrogen sulfide. We still get large populations of cyanobacteria, but after oxygen has been used, slowly, the development of chlorophyll would be the main light capturing pigment in plant organisms. And for the first time, oxygen was released into the atmosphere for the next 1.8 billion years. Lots of oxygen. And why I say the next 1.8 billion years? Because things would change again. And I hope you're still with me. Please ask questions, or if you disagree with me, let's see. I found this a very interesting slide about the changes of the atmospheric concentration of oxygen over time. Here you can see the beginning of life, 3.8 million years ago, and just about the time that we've said now, we see a rise in oxygen as we have the photosynthetic organisms starting to multiply. About 3.5 billion years ago, these cyanobacteria started to build what we now know as stromatolites. And once again, stromatolites are still alive. I'll show you a photograph just now. In their metabolic processes, they started to build upon layers of calcium carbonate, chalk, that we have today. And under these top layers, we had other bacteria, and sand grains, because they grew in the shallows of seas, was trapped in between them. So these dome-shaped colonies were formed, and today we see their remains as stromatolites. But stromatolites are still alive. About 2 billion years ago, the atmosphere was oxygen-rich. Now there was actually a shortage of carbon dioxide, and other bacteria now came to the fore, amongst others the purple bacteria, which we also still have today. They adapted to these low carbon dioxide conditions, and they started using oxygen, releasing carbon dioxide. Cellular respiration, right? Yes. These archaea, the original ancient bacteria and life forms, lived alongside the purple bacteria. And so there was a mutualistic relationship. And this is also the time when the archaea and the purple bacteria started swapping genes. Now, that usually happens during a form of reproduction. We also know about Lynn Margulis's theory of symbiosis, where bacterial cells swallowed, in inverted commas, other bacteria. That's why we know that chloroplasts and mitochondria today contain their plasmids of DNA. That's a story for another day. I was actually privileged to hear her speak. She's since passed away. She was the wife of Carl Sagan. Some of you might remember the original Cosmos. But anyway, it was one of the best talks that I've ever heard. Then if it seems that we jump from 2 billion years ago to 540 million years ago, you must remember that apart from all the comets and earthquakes and meteorites hitting Earth, Earth was actually a very boring place. Nothing much happened as far as life was concerned. It was a slow, but, colleagues, a very sure process. And about 540 million years ago, we have what is now known as the Cambric explosion, or the Cambrian explosion. And that happened because of the thinking is because of the levels of oxygen at that time. Now, there are two reasons for the many fossils we find of that time. And the one thing is that life forms, especially animal forms, started to develop hard parts, skeletons, shells, in other words, hard material which fossilized better. There might have been life forms before, that just didn't fossilize properly. And also, as I've said, the high concentrations of oxygen, which also allowed for bigger multicellular forms. Now, this photograph was taken of fossils from the Burgess Shale in Canada, and it was found many, many years before 1886, but it was really recognized and it was started to um, be a place of interest in around 1886. And we know that the Burgess Shale gives us an unbelievable variety of fossils dating from the Cambrian explosion. Life absolutely flourished because of the shells and the exoskeleton. And there you can see the oxygen concentration, which is today um, around 20%. It fluctuated between 15 and 35% of the atmospheric volume. Then, a little closer to our time, the first and also the biggest of all mass extinctions, the Permian extinction. And about 96% of aquatic life forms were wiped out, and probably triggered by the massive volcanic eruptions in Siberia that we today know as the Siberian Flats. Why the aquatic forms? Because life was mostly still in the seas, and also because of the effects of these volcanoes and the volcanic eruptions would have changed the composition of seawater. Our ancestors, mine and yours, survived. And there were some of the lucky few that did survive. It was a close call, or all life on Earth was absolutely extinct. It was also the time, about 200 million years ago, that the first mammals started to appear. Now, of Megazostrodon, it's a little rat-like structure. The fossils were first found in South Africa in the 1960s. Not a very nice picture. We don't have a photograph, obviously, but they were tiny rat-like structures, and because of their lifestyle, living in burrows underground, they were alive. As you can see, at the time of the dinosaurs, they survived the impact, the mass that caused the mass extinction that was the end of the dinosaurs, and that's why we are here today. They were also nocturnal, and so that's why they also survived the dinosaurs. So let's look at the first life forms. What were they? Where did we find them? I have to say thank you to Susara for formatting and tidying up my PowerPoint. I just continue and yes, thank you for your work there. This is a photograph of stromatolites at Shark Bay in Australia. It is a World Heritage Site. Access is prohibited because it's millions of years ago and fossils, but also living forms. This comes from the Precambrian. Remember, we said atmospheric gases, carbon dioxide, nitrogen, water vapor, and because of all the volcanic eruptions, fires, etc., also methane. So it was actually excellent conditions for what we have today, greenhouse effect. Now, after this Permian extinction, organisms were anaerobic. Oxygen levels were at a low. See there. And then the biggest of these fossils and the oldest, the bigger stromatolites, prokaryotic algae and cyanobacteria. This is also where once more, where your grade 10s have to know what a prokaryotic and an eukaryotic organisms, what they are. Okay, so let's go back to the origin and the early evolution of life. This was actually lots of animations. We took it out because we didn't feel like all the jumping around. Now, the oldest sign of life comes from Greenland chemical fossils. Remember, we talked about those first life forms that used chemicals and chemical photosynthesis to get their energy around 3.8 billion years ago during the Archean. Well, it's primitive organisms. But what's interesting in South Africa, we have the Barberton green belt. Now, the Barberton green belt, Barberton up in the Mpumalanga area, if I know my geography. Barberton has this rock with a greenish color that trapped fossils of cyanobacteria and first chlorophyll containing organisms billions and billions, millions of years ago. Then it was the time of the stromatolites. There you see the Proterozoic. There's another picture of where we find the Barberton fossils. Here you can see if we cut through, we get green belt areas up there. There we get some signs of early life. Oxygen levels are slowly rising. Here's those stromatolites. Now, when we look at our first metazoans, now the first metazoans were the jellyfish. And after in the Middle Cambrian, after the Permian extinction, we found an ice age that also almost froze life to death. And we have signs of these multicellular organisms in South Africa. We also have life forms of the first, or fossils of the first life forms with shells that we find in Namibia. There's some more information on that in the Mind Action book. Here's our metazoans. Yes, and they're still surviving today in more or less the same form. Fossils found in the Northern Cape. And then we move into the Carboniferous period or time. The Carboniferous was the rise of land plants containing a lot of carbon. Bockerfeld group of rocks contain lots of fossils like brachiopods, crinoids up here in KZN. And yes, we can see. There we've got the trilobites fossils. They, after the Cambrian explosion, they were top as far as numbers are concerned. Would you excuse me for a moment, please? I've got something at my gate, somebody who's not going to stop ringing the bell. 2 seconds. So sorry about that. Okay, so yes, this is what life in our seas looked like during these times. You can see variety, trilobites, lots of them. If you see photographs of trilobite fossils, I'm amazed at the variety that you find. And they were quite cute, from tiny ones to bigger, massive trilobites. There you can see the crinoids. We also have crinoid fossils around the Prince Albert areas. There's no more trilobites. There's brachiopods that you can see that you get here in the Western Cape and also around the Prince Albert fossil areas. South Africa is extremely rich in fossils. Okay, Gamkas Kloof Reserve, brachiopods, crinoids, This is the area that it looks like another crinoid. And some of you might remember Jannie Gerber. Some of you might even have been on this trip where we took teachers to go and visit, study the fossils. Then land, and we have the invaders that started to colonize land. You know about Tiktaalik, the first land animal, well, the start of land animals from sea to land, but it also happened with plants. And at the end of the Devonian period, and that's why I said earlier the Carboniferous with plants, we started getting plants on Earth. Now, it happened all over the planet, but we concentrate on our South African fossils. What was interesting that was about the time that the ozone layer started to being built up. And the ozone layer would have absorbed radiation, making it possible for plants to survive. Now, the first were the algae in the water, and then mosses, and just like we have today with succession, when mosses and later ferns started to colonize Earth, the smaller animals followed, arthropods looking much like cockroaches and even scorpions. There you can see the type of fern. We still find them today. Stellenbosch Botanical Garden has got a fantastic fern room, so to speak. And you can see so many primitive as well as modern ferns there. Go and have a look. Okay, more complicated, sometimes bizarre life forms in the sea. There you can see these are fern-like plants. Find them in the Eastern Cape. Now, quite often we see these patterns on rocks, and then it's because of different oxides, especially iron oxide forming. But yes, these are plant fossils. Okay, the Karoo we know was an inland sea, and that was around the time of Pangea or Pangea and the time of the breakup of the continents. Then we had in the Karoo, one of the best places to study the mammal-like reptiles. Now, just for interest's sake, and you can go and read, researchers say that today it's not suitable to talk about mammalian-like reptiles or mammals with reptilian characteristics. They give them specific names, most of them found in the Karoo Basin, known as therapsids or therapsids. We will talk about them. And in the end, whether we want to know it or not, these were ancestors of the mammals we have today, even us. There we can see more plants. This is students studying a fossil in the Karoo. A picture of Dictodon at a water source. We'll talk about them later. Another fossil, all from the Karoo area. This is the skull of one of these animals, and the distinction between reptiles and mammals starts with the ears and the orientation of the inner ear structures. Now we know today we've got many, many, many multicellular organisms that inhabit the earth. Unicellular too, but the development, so to speak. So evidence of this, ladies and gentlemen, we find in fossils. That's what fossils are to us, hard evidence. If you are an investigator, you need evidence. If you are a paleontologist, your evidence comes in the form of fossils. And it doesn't show us that there was evolution, also how it occurred. It tells us about changes in sea levels. It tells us about climate conditions. I was talking to my matrix about Darwin's voyage with Robert Fitzroy, the captain of the Beagle. When they stepped off the ship in Bahia in Southern America, they went for a walk and they saw a chalk ridge with shell fossils high up in the mountains in the area. To Robert Fitzroy, it was a sign of the biblical flood. But that was actually what started Darwin thinking about cataclysmic happenings on Earth. Because remember, as he started his voyage, Fitzroy gave him 2 volumes of Charles Lyell's book on the principles of geology. So he started thinking, it's one of the first bulbs that lighted up. So sometimes we see these fossils, remains, imprints, traces quite high up, and it's because of changes in the Earth's surface. Example, bivalves, snails, and ammonites. We see the Makatini in northern KZN, trilobites in the Karoo, whale fossils in the Saharan desert. I find that extremely interesting. But yes, we can go and see them today if you're ready for the heat. Now, paleontologists that I've referred to are the people studying these fossils in laboratories or where they are found. We just saw a photograph of such a study. This is a fossil, one of the Karoo fossils. We get many, 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 many of them. Few people are so lucky that you will walk and you will see this beautiful fossil. Now, I don't know if any one of you has ever been to New Bethesda, and just opposite, across the road from the Owl House, where Helen Martins lived and worked, there is such a fossil visible in what was once the riverbed, and there's now a stone plain. You can go and have a look if you're in that area. So paleontology is the scientific investigation of past life through geological time based on the study of fossils. Now, fossils, the study of fossils is important to our grade 10s. They don't have to know names of fossils. There are a few that we want them to know, but they have to know how fossils are formed. And they have to know what fossils are. And a fossil is the remains of ancient organisms that lived a very long time ago and where the remains are now preserved in rock. Fossilization is a very slow process. It takes about a million years. I always tell my grade 10s, if you want to become a fossil, it's not so easy. And as we've said, the oldest fossil, remember, the Greenland and Barberton Greenbelt fossils. And there you've got it. So how do we interpret the fossil record? We know that up to date, we have found about 300,000 different fossil species. Now, some fossils we have many, many, many samples. From other organisms, we might have a broken tooth, but still, it can teach us a lot. It showed us the type of living organisms that existed in the past. It helps us to understand where the living animals and plants were, when they lived, when and how they died, how evolution occurred over time, relationships between groups of organisms, and then the evolutionary line between the extinct animals and their modern and surviving descendants, and also a lot about the climate in which they live. Now, obviously, the fossil record is not complete. Not all fossils that are formed have been found yet. Not all organisms that die will fossilize. Some organisms, especially soft-bodied organisms, are not good to fossilize. We might find a mold here and there, but in most cases not. That's why plants don't leave that many fossils. We have pollen, for instance, and wood. But if you don't have hard parts, chances of fossilization not good, as I've said. And it doesn't say that if you die, you will become a fossil. So how are fossils formed? This is how you have to go about. First, you have to die in an area where it is cold and where there's very little, if any, oxygen. Low temperatures, little oxygen, if any, so that decomposition doesn't take place. There might be predators, scavengers in the water eating bits, but in most cases, these conditions will ensure that this dead animal will be covered by layer and layer of sand, sediment, in other words. And slowly over the years, and also under pressure, this sediment, the sand, will form rocks, sedimentary rocks. Those of you who teach geography or are interested or studied it will know exactly what we're talking about and how we go looking for it. So layer after layer after layer, and we have sedimentary rock. And millions of years pass. Now something happens, changes in the surface of the earth, might cause cracks in the rock layers, might expose some of these layers. I was privileged to be at a beach in the Southern Cape for last week's holidays, because you know that we're busy with term 2.2. And as we drove back, we drove through the De Toerskloof Pass, and time and again, I am in awe and wonder at the folded rock layers we find there. Also the Huis River Pass. If you drive from Ladysmith to, or Calitzdorp to Oudtshoorn, fantastic folds and changes in the mountains. And in that way, fossils might be exposed. We know that erosion plays a role, and when researchers go, paleontologists go to the Karoo, this is how they often find fossils, because of the erosion. You know the Karoo picture, these mountains with layer and layer and layer of rock, sedimentary rock, then it was all inland sea, then erosion dried up, and today we can find fossils there. Different types of fossils. Now, this is a fossil of a trilobite. They were in abundance about 570 million years ago. And this one is a mold, like a form we put in hot chocolate, letting it cool off, and then you got a little figure. And so this trilobite fossil specifically was a mold. This is the very well-known Archaeopteryx, an ancestral bird or a transitional fossil on its way to a bird. The hard parts were replaced by minerals. Here you can see an imprint of feathers, but the skeleton, hard part, the soft part of the body gone, but we have the skeleton. Now here is Archaeopteryx. This is, of course, an artist's impression. We don't even know what the feathers, the colors were like. We know that Archaeopteryx had teeth. That's not a bird. So that is a reptile characteristic. We know about the scales on the feet, and we know that birds still have scales on their legs. Also, and claws to their wings, some of the fingers, so to speak, that remained. The feathers then indicate birds. And we also know that the feathers in the first feathered reptiles were more for warmth than for flying. But today we have the birds. It's one of the oldest bird fossils that we have. We've since found similar fossils, another genus and species in China. But it's a transition between a reptile and a bird, and it has intermediate characteristics. So a transitional fossil is a fossil with intermediate characteristics between an older and a younger group. Older in this case, reptile, younger, bird. And they still show some reptile characteristics, the bony tail as well, and some bird characteristics. Not all of them, though. There was no keel bone. You know, that bone that's in a chicken is made up of lots of cartilage, hyaline cartilage, but to which the breast muscles are attached. And there you've got it. This is Archaeopteryx. Another transition fossil is Latimeria tolumnae. Now, you know the story of Latimeria, and it's also in the book a little bit more information. This fish was thought to have become extinct about 225 million years ago. And in 1938, off the coast at East London, one of these coelacanths were caught in the net of a fishing boat, and the captain had the savvy to immediately realize that this was no ordinary fish. Now, it was caught opposite the mouth of the Columna or the Columna River, and the captain took the fish, and by that time already in a little bit of a decomposed state, to the East London Museum, where he gave it to Mary Courtney Latimer, and she immediately recognized it for what it was, and she sent it to Professor J.L.B. Smith at the Grahamstown University of Rhodes. Professor Smith, in his time, recognized as one of the experts on bony fish in the world, and together they described it as a coelacanth, with the Latimeria in honor of Courtney Latimer and Cholumne for the river mouth where it was found. Now, people often refer to the coelacanth as a living fossil, which is not correct, for the simple reason that a fossil is dead and the coelacanth is very much alive. Now, after this found off the coast of East London, more coelacanths have been found at Sodwana, at the Comores, and recently in Indonesia at Sulawesi and Luzon Islands. And another species, by the way. So if we look at them, they are fins and scales like fish, the shape of a fish. But if we look at the pectoral and anal fins, it almost looks as if they are little legs. So yes, a transitional fossil with intermediate characteristics between fish and amphibians. This is a picture of Lystrosaurus. Lystrosaurus was about 95% of the therapsid population at some stage, and it's related to reptiles as well as mammals. Intermediate characteristics. And remember, these characteristics don't have to be spectacular. As I've said, these reptiles related to mammals. For starters, the structure and orientation of the inner ear. But our learners have to know how fossils are formed, the types of fossils, what a transitional fossil is, the three examples that we have here, Archaeopteryx, the coelacanth, and Lystrosaurus. In other words, what a transitional fossil is and their value. Now, this is a picture of 3 Dihyctodon. Well, we actually only know them as fossils, so this is also, after studying the skeletons, what artists came up with. Now, they are, in this picture, placed on the footprints of ancient Dihyctodon fossils. This is near Fraserburg, and these footprints then are what we know as trace fossils. The water hole is a giant footprint of a dinocephalus animal. In other words, we have lots of these footprints at Fraserburg in the veld. We also have marks of where animals were walking and their tails made lines in the um, sand, and the sand became hard over time. Today it's rock with these trace fossils. There's another footprint. More fossil type. There's another trace fossil. Something was dragged. It might have been an animal with a tail walking in circles. This is a mineralized bone where hard parts were replaced with mineral. Scorpion in amber. This fossil will be thousands and thousands of rands worth. Amber, comes from the gum of pine and other trees. And when insects were trapped in the gum and it hardened into amber, these fossils are priceless. And then mold, fossils of leaves, no hard parts, but there was a shape that was filled with in sand that was filled with rock. So we have a mold fossil. Now at this stage it is just before 4 o'clock, and before we continue with the dating of fossils, I would say 5 minutes comfort break. So I will start just before 4 o'clock again. So quickly go get something to drink, water or coffee, walk your turn, so to speak, and I'll see you at 4.
Lorraine, jy is op mute. Ek dink jy het jouself per ongeluk
Ek het myself op mute gesit want ons het nou eers 'n comfort break vir 5 minute.
Ekskuus,
Ja.
okay, doodreg.
Okay.
Doodreg.
Right, I think we can get back, get our seats. We've got some work to do still, but I won't keep you longer than promised. While we're waiting for everybody to settle, um, our grade 10 book also touches on, and it's part of CAPS curriculum, on fossil terrains. I've already mentioned a few. We don't have the time today to go into detail. We have exercises and informal assessments on fossil terrains in the grade 10 Mind Action book. Then also the human evolution, which is also a very short part of the grade 10 curriculum. We also don't have time for that today. But the good news is that on 5 August, the 5th of August, we will have another workshop on theories of evolution and human evolution. We will use the 2 hours for those 2 topics. Now, the history of life on Earth is more for grade 10 work. And we've said that today is for all grade 10, 11, and 12, because if you don't teach grade 12, you need to teach grade 10. And if you only teach grade 12, you need to know what they did in grade 10 and what they know by the time they get to you in grade 12. So yes, please attend that, whether you're grade 10, 11, or 12 teacher, please attend that session too. As I said, in that session, we'll talk about the theories of evolution, and it is good timing because it's just after school commenced for the 3rd term, and according to the ATPs, matrics will do evolution in the beginning of the 3rd term. So yes, there will once again be questions and a memorandum to the practice. And let's continue then. Right. Fossils can be dated. In other words, their age can be dated in many ways. One type that is used is relative dating. It's logical. All the fossils will be at the bottom of rock layers and younger fossils in layers at the top. Here you can see the trilobites, the rock layer in which the trilobites are found, much lower down than the shell creatures. I have no idea, probably brachiopods at the top. So that is relative dating. We can use this because we can date the rock layers. We can date the layers of volcanic ash, for instance, so we can see that a layer of volcanic ash, just let's say above the trilobites, we can look at the age and see it's maybe 520 million years old. Then we will know that a layer below, a sedimentary layer, will be older than 520 million years of older. This is relative. In other words, younger, older. It is not exact. A more, there you've got also got it. It is a very helpful way. I've talked about the folding of the rock layers earlier, and here you can see at 2 different locations, 2 different compositions of rock layers. If we have the same age of rock, we can know that the fossils in that rock are more or less the same age. So even though the layers on top of it and at the bottom might be different layers of rock, different ages, if we can date the rocks to, let's say, 200 million years ago at 2 different locations, in this case 200 miles apart, and in location A and location B, there are rock layers of the same age. and they contain the same type of fossils, we know that those fossils are more or less the same age. So that is also helpful with relative dating. Then a more absolute form of dating, more accurate, is radioactive decay or radiometric dating, where we use the half-life of radioactive isotopes to determine the age of rocks. Once again, not to the exact day and week, but more or less in a certain time span. What we know with radioactive decay is that half-life is the time it takes for half the radioactive isotopes in a rock to become non-radioactive. Let's say, I know that iodine takes about 4 hours. I once messed iodine on a much loved top, and I was devastated. And by the end of the day, but I was also presenting a course and I couldn't leave and go and put on a clean top. And by the end of the day, there was no sign of the iodine. So every 4 hours, half of the iodine was gone. Let's say I had 10 spots. After 4 hours, there were 5 spots. After another 4 hours, there were 2.5 spots. After another 4 hours, there were 1.25 spot. You get the idea. Now, we're not working with hours here. We're working with millions of years. Some radioactive isotopes have half-lives of millions and millions of years, some shorter. And we can use many of these different types. There is a section of it in the book where they show you many different types of elements. Uranium, for instance, argon, all of them very popular elements. You know about carbon dating. Now, many people have said in the past that carbon dating is not accurate. Therefore, this story of fossils being millions and millions of years old is nonsense. Yes, we have more ways to date older fossils because carbon dating these days are more used for artifacts. In other words, objects made by humans. Also for bodies, skeletons found in long ago graves. That is where carbon dating is a very, very helpful method. So they don't have to know the detail of the dating. You can give them a similar picture and ask questions to put it on a higher cognitive level. They don't have to know the detail, the absolute detail of radiometric dating. They must know what is used on the two types of dating. We also have something like paleomagnetic dating. We know that the north pole of the Earth, the magnetic north pole is shifting. And if we look at rocks and where the north pole of the rocks, where it points to, we can look at the shifting rate and we can look at where the rock's north pole points to, and we can make a deduction. Right. Then we get to a next topic, mass extinctions. Also important for the grade 10 learners to know. What is a mass extinction? How does it occur? What are the causes? What are the effects? What is the effect of whatever causes the mass extinction on the world populations of plants, animals, insects, you name it? In other words, what will the effects be of a mass extinction on life on Earth? Now, a mass extinction is the simultaneous elimination of a large number of species on a worldwide scale. You know, some of these extinctions even destroyed total families. And you know that a family can have many genera, many species. And it's on a worldwide scale. It's not just all the uh, um, eagles of this type disappeared from the Southern Cape. Well, let's hope it doesn't happen. But you understand what I'm trying to tell you. We've had many, more than 20 actually, extinction events or periods, according to the geological and fossil evidence. But there were 5 major events that have drastically affected life on Earth. I referred to the first one, the Permian, or rather the first big one that got rid of about 95% of organisms. The first one was at the end of the Ordovician period, then the end of the Devonian, then the end of the Permian, end of the Trias, and the end of the Cretaceous. Now, here you can see the number of families destroyed and some of these mass extinctions. Cretaceous extinction, 65, 66 million years ago. No one can say exactly what caused the mass extinctions, but there are 2 types of causes: intrinsic on the Earth itself, or extrinsic from outside the Earth. And there we can see that the intrinsic causes, volcanoes and ice ages, for example, and extrinsic causes from outside the Earth, meteorites. There, something happened. Now are we back? Right. So, as we continue, okay, it's hanging a little. Let's see. There we are. I've said a volcano is an intrinsic cause. A volcano can cause devastation. When Krakatoa erupted, the climate of Earth changed for more than a year. They talked about the year with no summer. It was a winter similar to a nuclear winter. It was devastation. And you know where Krakatoa is? In the Indonesian area. There was a man who painted the sunset in London every day for almost a year. And the effect of the Krakatoan eruption could be seen in his paintings that he made for more than a year. It's intrinsic, it's on Earth. First, when a volcano erupts, there will be dust and ashes blocking the rays of the sun. And depending on how severe the eruption was, it could last for a long time. We've had the volcanic eruptions in Iceland recently, also in Hawaii. You know the effects. Now, when dust and ashes block the rays of the sun, the earth will cool down. Now, sun not getting through and lower temperatures will inhibit photosynthesis. If photosynthesis is inhibited, in other words, stopped, tempo slowed, or even stopping, the food chains will collapse. Then organisms feeding on plants will die. The sulfur dioxide being spewed into the air will dissolve in water and it will cause acid rain. That will damage water sources. The carbon dioxide will cause a greenhouse effect. So after the initial cooling down, we will now have a heating up. There's a global warming, in other words, and it can lead to very high temperatures. What will happen is there's temperature differences between the equator and the poles today. But when we have this type of greenhouse effect, the temperature differences will be less. So the temperature all over the earth, or over the globe, will be closer to each other. And it's not a good thing as we might think. So it will also mean that ocean temperatures will be similar. And that will mean that ocean currents will stop. Now, currently, scientists are in two minds that the ice melt from the Arctic pole, the North Pole, will stop the great Gulf Stream from the Atlantic Ocean warming up Britain and those areas. Others say, no, it's not going to happen. But it did happen with a mass extinction. And then we get ocean stagnation. We don't get a circulation of nutrients and oxygen. We find that marine organisms will die. And that is a terrible thing. And so that was the cause of or the effect of the Permian mass extinction. But it will also happen on land, we'll see now. Now, a second intrinsic factor, in other words, something on land, on the earth, is continental drift going together with the tectonic plates. We know that the Earth's crust consists of 7 major and then several lesser tectonic plates. These tectonic plates move constantly, and they will have an effect on the Earth over very long periods of time. And here you can see the plates, the tectonic plates. Look at the big North American plate, top left, and the Eurasian plate, top right. And as you can see, the border between these two plates runs right through Iceland. Hence, the many volcanic eruptions on Iceland. Look at the Eurasian plate and the African plate and the Arabian plate. The three of those plates coming together in the Middle East. Remember how many earthquakes we get in the Middle East? And with a devastation loss of lives? Those earthquakes caused by the movement of those tectonic plates. Recently, we had a huge earthquake in the Himalayas and in Tibet. Also, loss of lives. Look, the Eurasian plate and the Indian-Australian plate, those two plates meet at the Himalayas because India is still moving into Eurasia, into the Himalayas. If we look at Africa, we will see that Southern Africa, where we are, does not lie on a ridge or on a border between plates or close to one. We do have our occasional earthquake, but not that many, and sometimes other causes. These plates move. Some of them move closer to each other, and some of them move away from each other. The mid-Atlantic ridge is where the South American plate and the African plate move away from each other. Joke you can make with your grade 10s to tell them that if they want to go and watch soccer in Brasilia, they need to start saving for their air tickets because South America and Africa is moving apart at a rate of, would you believe it, an average of 4.1, but they've calculated movements away from each other of up to 5.7 centimeters a year. And they can measure these movements by using the satellites that we have in space. If you look at the Pacific plate, you will see it on the left and on the right. Unfortunately, I don't have one where they join. That is the huge Pacific plate that causes the ring of fire where you have all the volcanoes. Now, you will remember, was it 2004 where we had the tsunamis in the Philippines or the Philippines? Look at the plates there and the Java Trench. Now, some plates move away from each other, but then it will mean that other plates will move towards each other. And plates moving towards each other will press and then the one will slip under the other plate. It's called subduction of the one plate. That will cause a huge earthquake. And if it happens in the sea, that is where a tsunami comes from. Now, the theory of these plate tectonics was first postulated by Alfred Wegener. Now, Wegener is regarded as the father of the plate tectonic from 1912, and everybody laughed at him. His best supporter was actually a South African geologist, Alexander du Toit, and there's a mountain in Antarctica named after du Toit because his advocacy led to the acceptance of this theory in the 1930s. Now, if we go back to these plates, you will see that Africa and South America is almost like puzzle pieces that will fit into each other. There's Madagascar that could have fit in there. We know, apart from the fact that we have the moving plates, we also have the continents moving apart from each other. And there we have it. Continental drift, volcanoes. So plate tectonics drive continental drift. And they can use laser beams and the satellites to find the direction of the plate movements as well as the rate of these movements. Okay, there you can see this is just for interest's sake. You don't have to know any of these. You don't have, your learners don't have to know them. It's a clearer picture, but these numbers you can see moving away from each other, moving towards each other at other areas. There you can see. Look at North America. These two plates are moving up and down. They are scouring against each other. And this, you can actually see it on land in North America. This is the cause of the earthquakes that every now and then will hit San Francisco. Look at Chile, on a line with its many earthquakes. And I'm talking about this because one of these earthquakes in Chile, they went on their travel through the, or let's say around South America. They did visit other places. Robert Fitzroy and Charles Darwin from the Beagle visited the governor and his wife at Valparaiso. The countries weren't united like today at that time. So they had dinner with the governor and his wife. And then they started looking at some of the islands in the area. And 10 days later, they got back to Valparaiso. And they found the governor's wife on a plank in the bay, drifting. They rescued her. And they found the governor, unfortunately deceased, crushed under the government house on mainland, and everything 10 meters higher than before they left 10 days ago. So you will see why I'm going on and on about this, because it has a huge effect on the earth as we know it, as it was, and as it will be when we're long gone. There we can see some of the diagrams, and we know that at first that all of these plates were together in the huge continent of Pangaea, or Pangaea as it's also pronounced. Then about 150 years ago, Pangaea had split into two northern and southern continents, Laurasia and Gondwana. And then Laurasia started to split, Gondwana started to split. And this is the current situation. How do we know that it was true? How do we know that continent split? Now, okay, Gondwana Actually, to say Gondwana means land of the Gonds. To say Gondwana land means land of the Gonds land. But just by the way, Gondwana consisted of Africa, India, Antarctica, South America, Australia, Madagascar, and a few other islands, as you can see. And yes, if you put them together, they can actually fit in together. Right, there you can see. Just a little bit of an animation. Fossils, one of our best pieces of evidence for the existence of Gondwana. Sorry, the writing not very clear. Cyanonatus, fossils found on South America as well as in Africa. Lystrosaurus, Africa, Madagascar, India, Antarctica. We have many of these therapsids and synapsids on Antarctica. Mesosaurus, fossil species, it's a freshwater reptile. South America, Africa. And the green, which we find in most of these, well, almost just about, Glossopteris, a tree fern, South America, Africa, Madagascar, India, Antarctica, and Australia. So we find these fossils on the continents, and that indicates that at some stage these continents were joined because the animals could move or the plants grew all over all of these continents. If we put continents together, we will see that there are marks on the rock. And these marks were made by the movement of glaciers. And if you look at this picture, that is where we find the marks, and this came from an ice age. And that brings us to the third intrinsic factor, ice ages. Ice age will cause, if water will freeze, the sea levels will drop, and it will reduce warm inland seas. But when lots of fresh water is frozen, you will find that the salt content, the salinity of the seawater will increase. The habitat is reduced. Nothing can live in this ice. So land species will move to the equator and maybe even north. So there's an increased competition for resources. This is the extent of the last ice age that Earth experienced, about 100,000 to 25,000 years ago. Cold. Extrinsic causes then from outside the Earth. I think, well, although this is a simulation, a computer-generated picture, I still think it's brilliant. Earth has been hit by meteorites ever since its beginning. The moon as well. We can see that if we look at the moon with the telescope. If we look at the moon with our bare eyes, we can see patterns on the moon. And use a telescope, you'll see it is impact craters. Now, actually, the moon originated from the Earth hit by a massive meteor. So much so that a piece broke loose, spun off in space, and because of gravity and the spinning, it turned into the roundish moon, and Earth returned and recovered to form what we know as our blue marble. This is just a few of these impact craters dotted all over the Earth. Vredefort in South Africa, there it is, was at some stage regarded as the oldest and biggest impact crater in the world. Now, recently, about a few weeks ago, scientists announced that another even older impact crater was found. I'm still waiting for more news. This crater can be seen from outer space. It's very much reduced by erosion. The town of Paris, there's the Vredefort area. Gulf station building, it's got a lot to do with the actual crater disappearing. But you can see it's about 2023 million years ago old, and the crater itself was 300 kilometers in radius. It is unbelievable. Now, when a meteor hits the Earth, massive amounts of stone and dust and smoke and ash will be ejected into the air. So once again, sunlight is blocked. Photosynthesis can't take place. Once again, food chains will collapse. Cataclysmic results, people. Tsunamis, flood waves, wildfires. We know that a meteorite hitting the Earth in the Yucatan Peninsula in Mexico caused almost all of Northern America and Southern America, the surface vegetation, to be destroyed by fires within 24 hours. Sulfuric acid, clouds in the atmosphere, acid rain, thick clouds, the Earth cooled down by 10 to 17 degrees. And we know that most of the dinosaurs were ectothermic. We don't use the term cold blood anymore, really, but to give you an idea, they couldn't be so active, so they slowly started to die out. Remember, this wasn't a single day extinction. It took about 10,000 years, but things were never the same after this meteor hit, comet hit. This is a less eroded crater, and it's found in Arizona, in America. One of the things that today is used as evidence for the fact that meteorites had this extinction effect is the fact that, yes, meteorites did hit the Earth. How do we know that? In rocks of the Cretaceous, about 65 million years ago, we find many deposits of iridium. Now, iridium is an element that is very scarce on Earth. It's found in space on meteors, sorry, and when it hits the Earth, these deposits of iridium remains behind. Shock quartz, black glass, glassy rock will be found in the rocks. Carbon formed under intense heat. You know, there's a worldwide layer of black sooty rock dating 65 million years ago. This soot was deposited all over the world. And the first inclination of this was from geologists in France, actually, when they did some digging for something totally different. And they found this layer and they dated the layer. Some more evidence. We know that the extinction of dinosaurs and other related reptiles, so weren't all dinosaurs, that they became extinct about 65 to 66 million years ago. We have fossil and geological evidence for that. The Chicxulub crater in the sea off the Yucatan Peninsula in Mexico in 1991, it was discovered, and this crater is about 65 million years ago. And there you see it. There's a crater, partly in the sea, partly on the land in the Yucatan Peninsula. What happens? If this meteorite hits, we've got the ejecta, vapor, ejecta, the solids, and melting at the bottom. And then you got the shock wave and the backlash. Breccia, broken pieces of rock, molten rock. There's a central uplift, fractured rock below that, faults in the rock, blanket of the ejecta that is finer gravel and rocks, and that is what we see around crater. Sorry. That is what we see around a crater. There you can see the ejector. Okay. Dinosaurs, they didn't see anything. And even today, we might look up and think it's a shooting star and the next thing will be gone. It happens so fast. We've got another extinction, by the way, which is the sixth mass extinction. And that is the one that is so different because it's caused entirely by us. We know that there's a huge number of organisms going extinct every year. Every now and then we have good news, but the bad news of species extinction is much more. We've included the website where you can go and look at more evidence and information of the sixth extinction. It's caused by human activity, global warming, temperature changes, greenhouse effect, the result of human activity. Ladies and gentlemen, there's always been greenhouse effect. The greenhouse effect is what makes life on Earth possible. It ensures that planet Earth is a Goldilocks planet, not too hot, not too cold. But too much of a good thing is bad. And it's getting to be Papa Bear's temperature. Too hot, and that is bad. According to the World Wildlife Fund, they calculate that the extinction rate of species, if no humans are around, is about 0.01 to 0.1% of all species. In other words, species do get extinct. But the rate currently, they judged it to be 10,000 or even 100,000 times higher. Are we listening to this? How long will we see this creature? There are signs now that polar bears are overheating because they have to swim long distances between an ice pack and the next ice pack. Ice packs crumble under them. And that is what I find actually quite terrible. So thank you for listening to us. Please go and have a look at the Mind Action textbook for grade 10 life sciences. Yes, I'm advertising it, but I'm advertising because I think there's lots of information that can be used. We have many exercises, not just for this chapter, for many others too. And there is a teacher's guideline available as well. We've got many exercises that can be used as informal assessment, homework activities, in other words, or class activities. And then each chapter is closed with an example of a formal test for at least 50 marks. Now, it is in the book. If your learners use the books, they will see it. But the point of those then is that it's a practice paper. It is on different cognitive levels and it covers the work in the chapter. So from my side then, yes, that is where we are, and I'm stopping the sharing, and here we are back. Rosal, we finished with our presentation, and thank you so much for attending.
Lorraine, thank you so much for this presentation. It was wonderful. I've learned quite a bit. And yeah, thank you for the time and effort you've put in this presentation. We really appreciate it. Just to let everyone know, we have recorded and we will share the recording and the PowerPoint presentation with you afterwards.
And you will get the questions, and you will get the questions and the memo, and the Afrikaans PowerPoint will be available soon, hopefully next week earliest.
Fantastic. Thank you, Lorraine. Thank you, Susara. We appreciate you. Until next time, have a good evening, everyone.
Until next time, keep well.